Anyway, that was the only thing I changed.
Is it NHD9?
It is.
Just
Let's
try my
see if
computer real
yours
quick.
works, and then we can see if that's the problem.
See if I'm really. Oh, my computer is picking up that it's plugged in.
Oh,
Well,
cool. All right.
teach off my. I got the.
Let me see if let me just try it again now that it's like talking, but stay here just in case. Okay. There it goes. Okay. Cool. Just need to be reminded. Okay. So we're going to get some intuition for inversion and then do some quantitative inversion. You're going to, I actually programmed in the Aug2 algorithm, the eigenvectors, you get a bunch of water. So this is the first page on the Excel spreadsheet. And all it is here, these are the coefficients on this really intuitive equation for chlorophyll, right? That's the band ratio. If you go to the next page, that's the eigenvectors. Those should look really familiar because I just plotted them for you. And so here they are, it's wavelength, and then they're all normalized to 400, except for obviously water absorption and water backscattering. This is where I determine the spectral slope of CDOM and AP. And if you average them, you can change those numbers and it will change the shape of these vectors here. You can also change the power or the exponent on the power law for backscattering spectrum, right? So you can change all of those parameters if you want. We won't do that initially. If you go to the blue water page, this is the measured spectrum for off the coast of Oregon into the gyre. And this is the measured spectrum. This will be the modeled spectrum. Don't mess with this, that's the equation. This is phytoplankton's CDOM, NAP, backscattering for large and small. This immediately calculates the measured minus modeled. And this is the square of the difference, so you can calculate the root mean square error and the correlation. So what you change is F over Q. You change what's in blue. So you can just add values here so that it will be basically the eigenvalue multiplied by the eigenvector. So if you put in 0.1, it's going to be 0.1 times this phytoplankton absorption. So your absorption at 400 would be 0.1, right? So you just change these coefficients here as if you are a linearly square or non-linearly square regressor. Okay. So what I want you all to do is to start adding values in here. And what's going to happen is it's going to change your model. It's going to increase or decrease your root mean square error. And it's going to plot for you what the estimated IOPs of absorption and backscattering. It will plot them here. Okay. So go ahead and do that and get your fit as close as you can get. And when you feel like that's as close as I can get, raise your hand and we'll start writing down some numbers. Does that make sense?
Are measuring our loss.
So R is just the correlation coefficient, which isn't really accurate. The root mean square error, we're looking for the root mean square error. We want that number to be small as possible. So whatever you're multiplying by, that's going to be your absorption coefficient of 400. So say for example you put in 10, then you're saying the absorption is 10 per meter. So part of what my goal of this is not to just have you mess around with Excel, but to also think about what are reasonable values for absorption and backscattering coefficients that can reconstruct that. And you've been measuring them for the last 2 weeks, so you should have an idea of what some absorption values might look like. you start to see bumps showing up where they shouldn't, you have to think about what's causing those bumps and what you want to try to get rid of. And sometimes you get rid of it, but you get rid of things that you want. And if you notice as you're doing that, it's going to automatically calculate the OC4 chlorophyll from the spectrum that you're modeling. So if you see that it's estimating a chlorophyll of 20, that might be that you have too high of absorption, spectrum absorption. So who's got a good RMS that they feel proud of?
No.
Next got one.
No, I was.
Okay. Oh, you're smiling.
Everybody said, no, the point of the problem.
I can get low numbers, but it's just not like,
Oh,
not really small.
yeah, but your RMS still. So look at your values here. That's 4 per meter. And you can't even see your spectrum here.
I was having trouble balancing the.
So this is blue water. So blue water is a gyre. So probably really low concentrations of everything, right? You have really high reflectance because you have low absorption. So if you can't get a spectrum, you're probably just way too high of IOPs. Okay. .004 RMS. What'd you get?
Well, I'm not, I want to keep playing, but right now I have 0.0035.
Okay.
I guess that's,
How quickly they fall. 0.005.
if you round up, it's the same.
Everybody's got the same level of significant digits. Has everyone got a modeled spectrum that they can see on the graph, which means that you have close to the right? Okay, good. I think my before, so we're on that. Which part? So many parts. I know, right? Yeah, that's the part I struggle with too. And you got basically exactly what I got. Yeah, you can't change water. It's the constant. Yeah, so if you switch up, you'll see those buttons. Yeah.
Should just be down, so that's water.
Yeah, and you got, yeah, I can't get rid of that PDA.
Oops, I also don't know how to get it.
Bit on that. So, I think,
Did you change?
yeah, ours is pretty, ours is similar. I think yours might be close. Yeah. That's good. This is another one, everyone's like, raise that. How can I do this with things that are very frustrating? It's frustrating, right? So then think about, if you can't get rid of something that you want, like what would you change in your eigenvalue? What is it that you think that these are eigenvectors? What is it that you think is not being well replicated by the eigenvectors that are provided, which again are just basic? If you look at the spectrum of measured minus model reflectance, it's going to give you a hint about what you're not doing well. Yes.
Oh, no, I'm just,
Excellent.
thank you.
Yes.
I guess I'm just confused about
Well, you modeled it so that there's not very much chlorophyll, which is accurate,
how.
and have just like very low absorption in here, and also more large particles compared to small, or more small particles compared to large particles. Does that make sense for the open ocean?
It does.
Yeah, exactly. So that all makes sense. Like there's,
Oh, awesome.
the scattering will be more fluid scattering, than something flat scattering.
Ah, okay.
Right?
Yeah. Okay, thank you.
Yes.
Because I guess I'm still like, I'm here and then I understand.
Create. Yeah. I don't know if we can get rid of the weird thing.
I did change this actually.
So as starting values, you want to think about phytoplankton being on the order of 0.008. Yeah. Yeah. So I had really low. I had really low phytoplankton, but it gave me 0.05 chlorophyll, which is about what was out there when we measured it. And then I just partitioned CDOM and NAP the same. I said there were no large particles out there. I just had all mine in small particles, right? And I got a pretty low value, but you see that I just don't do that well in the blue. So Nick, what did you have?
I beat myself again, so 0.00229.
Ah, so what did you have for phytoplankton?
0.0098.
Okay, and?
0.004.
Okay,
0.001.
yep,
0.0022.
0022.
0.0001.
Ah, right? So what it's saying is that we have too much backscattering in the red and not quite enough absorption in the, or too much absorption in the green and not enough absorption in the blue. So there's definite features in here, many of which look phytoplankton-like. And what I would say is that in the open ocean, we have a lot of cyanobacteria. Cyanobacteria have pigments here, which would bring this down. And that is definitely not in the model, right? So you would want to maybe add an eigenvector for open ocean phytoplankton. That would be more appropriate. And then it would give you a better fit, but still not bad.
Sorry, where did you get these eigenvectors?
These are the same ones that I just showed you in the lecture this morning. So the eigenvectors, if you go here, they're just these eigenvectors, the ones I've been showing you, right? So phytoplankton is just the average curve. CDOM and NAP absorption are just exponentials with a spectral slope that I defined by 0.018 and 0.01 respectively, right? And then the particles are just defined for being spectrally flat or having a slope of -1. So one could change those. I would make sure that you write down what's there so you can recover it, but changing that might help you. But don't do it yet because we're moving on to green water. Okay, go to green. Give it a try. I'll leave up the blue. Oh, I was reading the wrong thing. One thing to think about is that the chlorophyll was estimated at 0.05 or measured at 0.05, and the estimate was an order of magnitude higher than that. Okay.
That was this.
Yep.
Okay, that.
So if you do an order of magnitude less phytoplankton, you get the right chlorophyll based upon the reflectance ratio, right? But then look, I have to change everything else. So this is what I got to get close to the chlorophyll, but then having to balance. So it did better in the green, but it did much worse in the blue. The O's and 1.8.
No. 2 O's.
2 O's and 1.8.
0.00108.
00108. Okay. 3096.
Ooh, ouch.
Is your chlorophyll close to the estimated chlorophyll, your estimated chlorophyll close to the real chlorophyll?
0.
There's estimated dynamics.
Yeah, no,
How close to them?
Oh. Yeah, mine's really up too.
Yeah, right, exactly. So over one, so higher RMS, but. So it looks like you're still missing something here, so. So see if you can get this, that's okay, as long as the chlorophyll is close. Remember how we're supposed to measure chlorophyll? What's our uncertainty in chlorophyll? Right, and this was uncertainty in chlorophyll measured 30 years ago.
Two.
Ooh, it looks really nice. Okay, yep. So then there's the question, right? Is that, that's what you need to validate. Right? So you're only validating chlorophyll, but you really want to do validated venous absorption, which I didn't go. But that's one of those things where you can find a local minimum in the regression, even in an automatic, even when it's done with the computer, not just and is it giving you the right one? And so when I do anomaly estimation, I use the 11 Bergman card method because it actually looks for fitting at features as opposed to minimizing the overall spectrum. It minimizes the in place of the high gradient. And so it's tuned.
0009.
It's tuned to be able to hit features.
Oh, you did?
What's your chlorophyll?
Wait, 00087 is the best right now. Yeah, my chlorophyll's well.
My chlorophyll's right on,
Yes.
9.0013.
Accuracy.
Okay.
So I got
Yeah.
3 zeros, 98, and my chlorophyll was off by 0.03.
Wow.
But some of you had some better fits in here, and I can see that, I have a little bit too much, maybe CDOM absorption, right? And so, but you can see that it's got sort of a nice bit of shape. It's catching the dip here, catching the big shoulder here. It's a little bit too much back scattering here, but not bad. All right, do the last one, and then we'll go on to being able to do it. So you should be all good on this. It's like nail it the first time. You guys can save this on your own computer, right? Yes. So that's what you do. There we go. Okay, thank you. The other thing about the yellow water is it's gonna look similar to what we have out here, so you're kind of also almost fitting our plane. So you can modify this for radiance reflectance, just update it instead of 0.3 degrees to 0.9, 0.9, 0.9 or something. Grab over here and add your own base factor changes. To entertain your friends, parties, good party trick. Really gets the conversation going. Gets people off their phones. On their computers. You could ask Guillaume to put it onto a phone app.